It's a pleasure to have Matheus here with us today. Matheus did his undergrad and his master's in Viçosa. Then his PhD he did in Rio in CBPF. And he worked with modified theories of gravity and QFT in curved spacetimes. Then he joined the Institute for his postdoc in the astroparticle physics group, and he's been working on the interface between cosmology and particle physics.
Yeah.
This is what he will be talking about today. So please, Matheus, take it away.
So thank you so much for the very nice presentation. Let me start my time because I talk a lot usually. And so I have three main purposes with my talk today. The first one is I want to show you or present very convincing arguments of why we need to talk about particle physics in cosmology. And I mean, the thermal evolution and the observational imprints we have in cosmology, to explain precisely all those observations, we necessarily need to use particle physics. And the understanding of particle physics is essential for the evolution of the universe. So I'm going to spend a lot of time talking about that. It's the first part of my presentation. And the second part, I wanted to show you some of the works I'm having doing here at the Institute in this first year of my postdoc. And perhaps the third part, I wanted to show you and talk a little bit of how the Institute helps me and it's connected with the initiative of international community in what says respect to the research in particle physics and cosmology, right? So, when I joined the Institute back a year ago, this is basically our group. We have one brand new postdoc. It's end of July, if I'm not wrong. We have 2 PhD students, 4 master students, and 4 undergrad students. And now the group grows a lot, all right? We have now 4 postdocs. The master students are promoted to PhD students. We gain another PhD students as well. Some of the undergrad are also promoted to master students. We have 4 masters students, 5 undergrad students. So I mean, it's the group is growing a lot in this last year, and I think that this is this not happening just with the astroparticle group, but I think that's a combined effort of all the institutes. You just need to look to the board of the staff, our staff, to saw how much people we get in this last year. I'm sorry for those that are not in the picture. It's very hard to get a picture with everyone, actually. But basically, this is the structure of our group. So it's a lot of people. We forgot some of them. I'm sorry for that. It's really a lot of people. I'm going to put Amanda here. She's not here, sorry. And so, without further ado, I wanted to start with particle cosmology, or the importance of particle physics in understanding the cosmology. Basically, when we say about cosmology, we are talking about understand our universe and the evolution of the universe, basically. But as I'm going to show, particle physics is very important because in the beginning, if someone do not understand very well cosmology, do not understand very well the evolution of the universe, can think about that's 2 completely different topics of research. When we say about particle physics, we think the first thing that comes up in mind is the collider physics, LHC and other colliders. And when we say about cosmology, we think about the universe, the general relativity applied to the evolution of the universe, Friedmann's equation, but essentially, these large scales, and when people think about particle physics, it's small scales. But what I'm pretend to show you is that to understand cosmology, to understand physics, the evolution of the universe and physics at large scales today, we need to concern about the fundamental interactions that takes place in particle physics, all right? This is very important. So basically this is a standard model of particle physics. I think, okay. And I mean, this is the main Lagrangian of the standard model. We have this the gauge terms. We have some Dirac terms here for the fermions, Yukawa couplings. We have the terms of the Higgs. This is what we know our standard model today. But this is there's almost a century of research, a century of combined the efforts of the international community in order to get this Lagrangian. So it's very hard to get this Lagrangian here. And in order to understand the particle physics, we need to, I mean, it's good for us to go back to the history of accelerators. So in the early 50s, we got some of GeV energy, billion of electron volts. So that's what this collider is called Bevatron. It's just, one of the pioneering particle accelerator techniques that used in this collider, and it was very important to detect antiproton. And as time passes, we have a lot of colliders, and the energy scale usually grows a lot. Today we have something about a TeV scale. So I mean, we passed to the SLAC in the 60s with the deep inelastic scattering extrudes, showing the evidence of the quarks, which is really important in order to understand the baryonic matter. That's a crucial aspect, a crucial thing in cosmology. So still in SLAC, we have the Spear, discovered the J-psi meson, helps to understand the theory of quantum chromodynamics. That's very important to modeling the thermal history of the universe. We have the SPS proton with energy around, I mean, it grows a lot, the energy from the beginning of the Bevatron, and detects the W and Z bosons, and help us to understand the electroweak unification, which are essential in order to understand for the process that formed the light nuclei in the beginning of the universe. The neutrino-lepton interactions are crucial in order to understand what we call of BBN. Big Bang, basically is the acronym for Big Bang nucleosynthesis. We have the LAP that help us to limit the number of light family neutrinos to 3. That's, again, it's important to understand cosmic microwave background and Big Bang nucleosynthesis. The Tevatron, now it's around TeV scale, detect of the top quarks, very important for the Higgs physics, and there is a lot of implications for the early universe phase transitions. And more recently, it's not passing. Okay. We have the LHC that detects the Higgs boson. Sorry, this is TeV scale, right? That's a mistake here. It's TeV, both here are TeV scale. And I mean, in addition to help us to understand the electroweak baryogenesis in cosmology, it puts strong limits on beyond standard model physics, like SUSY, dark matter, long-lived particles. I'm going to talk a lot of long-lived particles in the second part of this talk. And we have future plans that high luminosity LHC that will improve the measurements of the Higgs, W, Z, top couplings, and will make some better searches for dark sector particles. Very important for cosmology, because when we talk about cosmology, the dark matter is very, very important. So understand this phenomenology or put some limits on dark matter models helps a lot in order to understand the evolution of the universe. And we hope in the future there's a FCC, ILC, and other colliders, but we hope to obtain this 100 TeV energy. And just for you have some idea of this is here 27 kilometers are the LHC, and the FCC is planning to have 100 kilometers. So it's a lot bigger than LHC. So it will help us a lot for look for new physics at this scale, 100 TeV scale, and will allow us to assess heavy particles that are connected to inflation, neutrinos physics, heavy neutrinos, and especially dark matter. So we have a combined effort, almost a century already passing by, and we are planning to make a lot of efforts still in the studying this collider physics. And because it is important for particle physics, but in addition, it's very important to cosmology. So, after this almost 1 century from the Dirac's groundbreaking paper about the positrons, predicting the antiparticles, what is the standard model right now? We have 6 quarks, up, down, charm, strange, top, bottom, 6 leptons, electron, muon, and tau, and its neutrinos. We have 5 carrier forces, basically are the gauge mediators. We have the gluon, the photon, the W's and Z, and this is strong force, electromagnetic force, and the weak force. And we have the Higgs that interact with some particles of the standard model and allows particles to have mass, acquires mass via the Higgs mechanism, right? We have this is the fundamental group of symmetry of the standard model, the SU3 cross SU2 cross 1. So this basically, after all this effort studying particle physics, this is the standard model of fundamental interactions. That's the best model we got, and it's amazing how we get that, and the most of the predictions of the theory are correct, and how a lot of technology we built in order to understand the fundamental interactions of the fundamental particles in the universe. But the life is not just sunshine and roses, so we have some deep problems regarding the standard model to be solved yet. We have the hierarchy problem. I mean, why the Higgs has the 125 GeV mass? Why isn't greater the mass of the Higgs? Because of quantum corrections, especially the ones coming from the mass of the top quark. The Higgs mass in principle should be a lot bigger than the 125 GeV. So some research, some directions of research indicates to SUSY, supersymmetry, in order to cancel out some of the contributions, the loop contributions, and allowing the Higgs to have that mass. But as I show, LHC puts strong constraints on SUSY models. So, I mean, we do not know yet very well why the Higgs has its mass. We have what we call a strong CP problem. That's basically the strong interactions allows some terms in the Lagrangian, these terms generate some, would generate some dipole moments in the neutrons, but measurements do not show or show the very small dipole moments, and this implicates that we could have another term, a theta term, in order to correct, to explain these small values, and this is connected to the axion physics. We have the flavor puzzle, why the families of leptons and quarks have their masses, because we have the difference of the masses between the first, second, and third families of the standard model have these exactly so big discrepancies. We have the problem of matter-antimatter asymmetry. We know that neutrinos have mass, but according to the standard model, neutrinos are massless. Also, we learned a lot in this last century. However, there's a lot of problems we need to solve yet. The standard model is not a complete model. That's why we need new colliders. That's why we need to understand there's a lot of problems we need to face in the future, right? And in particular, we do not know, the standard model do not accommodate the dark matter. And dark matter is essential for explaining cosmology, correct? So I'm going to focus on the dark matter problem and its connection with cosmology. So basically, this is the standard model of particle physics. On the other hand, we have the standard model of cosmology that we call lambda CDM model. That's the most robust model we have to describe the evolution of the universe. So have some assumptions. We assume an isotropic and homogeneous universe at large scales. So we use a Friedmann-Lemaitre-Robert-Walker symmetry in order to explain the expansion of the universe. General relativity governs the dynamics of the universe. So if we apply this metric, the Friedmann-Lemaitre-Robert-Walker symmetry, to Einstein's equations, we got what we call Friedmann equations, that basically equations to explain the evolution of the universe. And we assume that the primordial perturbations generated by early universe process, like inflation, are Gaussian. So those are the assumptions of the lambda CDM, all right? And this is the picture we have today. We have 68% of the energy, of the content energy of the universe is dominated by what we call dark energy. We do not know very well what dark energy is. 26% is dark matter. It's very different of dark energy. 5% is what we call baryonic matter. Basically all the particles of the standard model I showed a couple of slides ago are here in the baryonic matter. All the stars, all the galaxies, everything we know, the visible matter is just this small amount of, represents a small amount of the universe. And we still have some small fraction of radiation that's basically due to photons and neutrinos, right? And it's this model is widely accepted. Why? Because it explains a lot of the observational phenomena, right? The cosmic wave background explained by the lambda CDM model, the formation and distribution of large-scale structures, the baryon acoustic oscillation, the abundance of light elements. So it's a robust model and explains a lot of the observational phenomena. So it's what we call the standard model of cosmology. But again, there's not all roses. Sorry, I'm going to talk about dark matter first. So why we need dark matter? Basically, we need to, first of all, we need to understand the nature of dark matter. But dark matter is very important because if we consider just the baryons in the universe, we cannot explain some fundamental phenomena that is observed. For example, the galaxy rotation curves are not explained just by the presence of baryons itself. We need to account for a non-baryonic, non-luminous type of matter to explain why the rotation curves are as we measure. So some gravitational lensing shows that we need extra matter, especially dark matter, in order to account to the curvature because of the bending of light. Shows a presence of a lot more mass than we can actually see. So there's some kind of dark matter. And to explain cluster dynamics, we need also dark matter. So every place we look at the universe, we have the presence of matter that's not luminous and not baryonic. So we need this dark matter. Well, it provides what we call potential wells for galaxies and clusters to form. And the acoustic peaks of baryon acoustic oscillations or the acoustic peaks of CMB are affected by this dark matter. Here, determines the position and the height of the CMB peaks. So, I mean, some people think that perhaps we do not know very well general relativity. We do not have a complete theory for cosmology. And the fact that we have just 5% of baryonic matter, and we have this 68 and 20 of dark energy and 27% of dark matter, actually are a misunderstanding of our universe, of the laws of gravity at large scales. That's not actually true, this argument, because if we look to different types of observations, we need the presence of this dark matter. I mean, we cannot explain all these facts here just with alternative theories of gravity. Probably we need some alternative theory, some more fundamental theory of gravity to explain gravity at quantum scales, or either to explain dark energy, for example. That's a problem. Some theories of some alternative theories of gravity looks to very promising to explain dark energy. However, they do not explain dark matter. If we try to explain one of those aspects here with some alternative theory of gravity, we have a lot of problems with all the others. The others evidence of dark matter. So we solve one problem, but we create a lot of other problems. So dark matter is necessary, and that's why people are looking forward to find dark matter or to put some constraints on dark matter models in colliders and also in cosmology. So but again, I think that's if we study the history, the thermal history of the universe, it's more elegant. It's to understand how we need particle physics, all right? There's a deep connection between particle physics and cosmology. So these are basically the different time scales of the universe. So we have an initial period of exponential expansion. We call it inflation. It's the energy scale is around the grand unification theory scale. It's moods anisotropy generate quantum fluctuations, and those fluctuations seed the formation of structure in the late universe. So we have after the inflaton field, after the period of inflation, the inflaton field decays and fills the universe with hot plasma of particles. So this happens around 10 to the 15 GeV. And as the universe expands, it cools down, and around 100 GeV, we have the electroweak symmetry breaking. So we start to have the standard model particles. We start, after the electroweak breaking, we have the WZs, electrons, quarks, every particle of the standard model. If we keep following the expansion of the universe, the universe is still cooling, so the temperature drops a lot, and we start to have the hadron era. So the quarks and gluons start to form what we call of hadronic matter. that's basically, in cosmology, are basically protons and neutrons. And later, approximately 3 minutes after the Big Bang, we have what we call Big Bang nucleosynthesis, that the formation of the light nuclei, like deuterium, helium-3, helium-4, and lithium-7, the nucleus of these light elements here. And after that, we have recombination at this period here, where the electrons and protons, they form neutron atoms, and the photons, they decouple from the matter. That's letting this imprinting of the cosmic microwave background that we observe today, and we can use this observation can use to understand the evolution of the universe. This happens 308,000 years before the Big Bang. And after that, almost a giga year, 10 to the 9 years, we have the formation of the galaxy clusters and cosmic filaments. And finally, we have in the present day what we observe today in the universe. That's we are 13.8 giga years after the Big Bang. So, in order to get to today, we need to pass to all those processes out to these important times of all these eras of the cosmic evolution, and particle physics are fundamental in these initial eras here. So the initial eras let strong imprints on CMB, for example, on large-scale structures. All the cosmological observations are, we have the imprint of the particle physics dynamics in the beginning of the universe. So if we look today to the cosmic microwave background, for example, we have the access to the history, to the early history of the universe. And because of that, we understand particle physics. So what I'm saying is that if we have a different model or a different particles, different if we have other types of particles here or other fundamental theories, we would have different cosmic evolution, all right? So it's very important to understand the particle physics in the beginning of the universe. So we have some problems in the lambda CDM model. The nature of dark matter itself is a really big problem. We do not know yet. We try to understand, but we do not have sure of the nature of dark matter. We have the Hubble tension. And, the universe is expanding, but we have some tensions between different observations of the universe. The late time and early time measurements are in tension regarding the value of the expansion rate of the universe today. We have the lithium problem, the primordial nucleosynthesis. We explain very well, the Big Bang nucleosynthesis explain very well the abundance of deuterium, helium-3, helium-4, but we have some problems with the lithium. We have some small scale problems like the missing satellite problem, the cusp core problem that are associated to the nature and perhaps the interaction properties of dark matter. But what I wanted to show, what I wanted to explain here is that the thermal history of the universe is deeply influenced by particle physics process. I show you we have the standard model of particle physics, but there are still some problems, fundamental problems with standard model, all right? So if we do not have a complete theory for the particle physics, we need to beyond standard model physics to explain some phenomena. And those particle physics influence the cosmic evolution. We probably a lot of those problems here in the lambda CDM model can be treated if you understand the physics beyond the standard model of particle physics. I mean, if you understand, if you have some extra particles in the beginning of the universe, like some SUSY models or so other long-lived particles, if we have accounted for the nature of dark matter itself in the beginning of the universe, perhaps we can understand a lot of the problems we are facing with lambda CDM today. So I mean, I like to think that probably if we addressing the problems of some standard model of particle physics, we essentially will address as well the problems in cosmology. There is a deep connection between the problems in standard model and the problems in cosmology. So, for example, the nature of dark matter itself. If we go to a beyond standard model physics to explain the nature of dark matter, we can use like long-lived particles to produce the dark matter, WIMPs, weak interactive massive particles, despite the collider searches do not appoint, excludes a lot of the parameter space of the WIMPs. We have probably axion physics, sterile neutrinos. To explain the Hubble tension, for example, we can use extra relativistic species like a long-lived particle, dark radiation at the beginning of the universe. To explain the lithium problem, so the decays of azatic particle can alter the Big Bang nucleosynthesis and perhaps can solve the lithium problem, like long-lived particles, gravitinous, neutralinos, sterile neutrinos. And the small-scale structure problems, if we understand better the nature of dark matter, we can understand these small-scale problems. Probably they are showing that maybe a non-cold dark matter particle are essential in order to explain those problems, right? So, in order to understand, to lambda CDM model, we need to go beyond the standard model of particle physics. And that's exactly what the international community is doing or is planning to do right now. We have some collider searches regarding this respect. We have LHC, as I said, looking for dark matter mediators, looks for supersymmetry, exotic Higgs decays, direct detection experiments, aiming to observe WIMPs, axion searches, neutrino experiments like DUNE or Hypercaminho-Kandi, Juno, to measure the precise oscillations and mass ordering of the neutrino masses. So it's this is in particle physics essentially. In cosmology and astrophysics, we have the CMB missions like the Planck mission. We have a lot of data. We have the next CMB mission, CMB S4, the little bird. That aim to improve the constraints on H0, the Hubble parameter that measures the expansion rate of the universe, neutrino masses, dark radiation, possible observe the B modes of the polarization of CMB produced by gravitational waves because of the inflation, primordial gravitational waves. We have some large-scale surveys like DESI, Euclid, Vera Rubin, etc. This 21 centimeter cosmology and multi-messenger approaches. I like this here a lot because it combines gravitational wave physics with high energy astrophysics and possibly some high energy physics models, some particle physics models. And the idea is to use this multi-messenger approaches to test these lambda CDM extensions and also the extensions of the standard model of particle physics itself. So this is the part one. I think I can stop a little bit for questions if anyone has any question.
I have a question. What would be an sterile particle? I never heard of it before.
Basically, the sterile neutrino is a neutrino that do not interact via the weak force. Perhaps you could have a very massive neutrino, but it not interacts with via the usual mechanism that neutrino interacts with the leptons. So we call it sterile neutrinos. There are some models like the model of to explain the mass of the neutrinos, we call of seesaw models, some models to explain the neutrino masses. Some particular models, the usual idea of the seesaw mechanism to explain the mass of neutrinos is to consider another right-handed neutrino, very heavy neutrino, and some particular models considering that this type of neutrinos, these right-handed neutrinos, are sterile neutrinos because they do not interact in the usual form.
The neutrino. So in short, in short, is a neutrino that does not interact with the W and Z boson. Period.
More questions? So that's what the international community is doing. That's the relation between particle physics and cosmology. In the part 2, I'm going to show a lot of the works we have doing here at the Institute. I'm particularly working with dark matter decay in the ERA universe. In this dark matter decay can solve some problems in the I show you in the previous slides, the lambda CDM models. So the first tension we got is the Hubble tension. It's a tension between the late time measurements and the early time measurements. I think that's not appearing here, but we can saw the bars here. So basically, in the beginning, we have late and early time measurements, and the error bar of the measurements are too big. So what people think in the beginning here is that as we refine the measurements, we will decrease the error bars, and consequently, at the end, these measurements will coincide to some value. But this is not exactly what happens. Actually, as the time passes, the late time measurements obtains a value, especially this collaboration here. It's called Schulz, that use Cepheids and supernova to obtain the value of the H0. And the early time measurements, especially the ones using the Planck data, converge to a lower value of 67.27 kilometer per second per megaparsec, and we have a difference of about 5 sigma between those two measurements here. So we have a tension between these measurements that use this we call of late time measurements and these early time measurements here. So basically, to understand the both measurements, the Planck measurements here use the anisotropies of the cosmic wave background, and we make the fit of the power spectrum of the cosmic wave background. We use 6 parameters to obtain this fit, and we can obtain the value of H0, the Hubble parameter, today using this the fit obtained, the values obtained of these parameters here in the fit. So we can obtain a value using the data of CMB of 67, more or less 67 per, that's a low value, 67 kilometer per second per megaparsec. And the late time measurements, they are model independent. The early time measurements, they use the lambda CDM model necessarily to obtain the value of H0, while the late time measurements, they use, they measure the Hubble constant, this Hubble parameter here, using local observation of Cepheids and type Ia supernovas. So independent of the model, and the value is it's looks like that's not such a big difference, but it's very significant, the errors, and so it's attention because it's beyond the 5 sigma cutoff. So we have two possibilities here. First possibility is that the systematic errors are affecting the late time measurements, and this can lead to values to higher values of the Hubble parameter. And we have other problem that's another possibility that we need to go beyond the standard, beyond the lambda CDM model. So we need new physics is required in order that if we account for this new physics in the lambda CDM model, we can have some higher values of the Hubble parameter that comes from the CMB. So basically, we assume this second approach here that maybe we need new physics. We need to go beyond the standard model of cosmology, and that's basically what we did. We assume that in the radiation dominated era in the universe, we have I put here some decaying cold dark matter, but can be not necessarily needs to be a dark matter. Can be a long-lived particle, can decay into some hot dark matter plus a neutrino. Sorry. Okay. There's a delay in the. Okay, nice. So the idea is that we will have a long-standing particle that will decay. This particle here is very heavy, so we have the mass of this long-lived particle is much greater than the mass of this hot dark matter here, this dark matter. And because of that, since the mass here is very big, this particle that will be generated, this dark matter particle that was created by the decay of the long-lived particle, will be relativistic. So in this sense, we say that it will be hot because it's relativistic, all right? So the idea to model this, we call of lambda CDM model plus an effective model, we assume that the radiation at the beginning of the universe just do because of the photons and to neutrinos. And we assume the presence of this extra particle, this extra radiation, the extra source of radiation at the beginning of the universe. And we can reparameterize the extra radiation in terms of the number of neutrinos. We put here some extra number of neutrinos. When we reparameterize the extra radiation in this form, we can observe that the radiation energy, the density energy of the universe due to radiation is just equal to the radiation of the photons plus the radiation content due to one neutrino plus this N effective here. That's basically the number of neutrino families. So the difference is that in the beginning, we have just 3 families of neutrinos, all right? And here in the end, because of the extra source of radiation, we have this. We have a different number. We have a very similar, but we have this n here. The number of neutrino families not necessarily need to be 3. Can be greater than 3. All right. So it in this sense, this extra radiation mimics the effect of the neutrinos in the universe. All right. And basically, this number of we call of relativistic degrees of freedom, basically the number of the neutrino families plus this extra, this delta n effective, that is the extra relativistic degrees of freedom because of this extra radiation here. So that's why we have this decaying dark matter model. We have this long-lived particle decaying into dark matter and a neutrino. And since this here is very massive, the mass is much greater than the mass of the dark matter. So the dark matter here is relativistic and can be the source of this extra radiation at the beginning of the universe. So the nice thing to observe is that allowing this value of n here, or n effective here, to vary a little bit, we can show that this middle value here comes from the Schulz, the late time of measurements, the collaboration that obtains the 63, more or less 63 kilometer per second per megaparsec. And allowing n effective to vary, we can observe that, for example, the data of Planck is this is the central value here. For example, is the value of the H naught obtained by Planck by allowing this n effect to vary. If it's greater than 3, we have a closer value to the data obtained by the Schulz. In this sense, we can not solve, but we can alleviate the tension between these two collaborations. I mean, it's we have a problem, and we have we do not understand very well the nature of dark matter. So, I mean, imagine that we have this extra particle in the beginning of the universe. We can explain we can alleviate this long-standing tension in cosmology. I think I'm going to skip all the calculations here. I'm just showing that we use just relativistic dynamics. It's not very hard to show that we can write this delta n effective here, assuming the decay. We can write this delta n effective here in terms of the particle physics parameters. So we have the lifetime of the decay. We have the moderate to Doppler mass ratio, and we have here a f. That's basically a constant that accounts for the dark matter produced, the percentage of dark matter, of the overall dark matter produced by this mechanism of decaying dark matter. So we have a lot of dark matter. That dark matter needs to be cold, usually to a structure to form, but we can have a small amount of hot dark matter, and there's what this f parameter here it's accounting. That we have just 1% of all the dark matter is due to this mechanism here. So, as I said, a majority of dark matter must be non-relativistic. We have a cutoff of the maximum of 6% of the dark matter can be what call of warm dark matter, and we assume a conservative value of percentage of just 0.01. I mean, we have just 1% of all the overall dark matter is produced by this mechanism here to not disrupt the structure formation. So we can use Big Bang nucleosynthesis because it is very important, because we are assuming extra beyond the standard model physics in the beginning of the universe, but we have very good observational data. So the lambda CDM, it explains a lot of the cosmological data. So if we are assuming some extra model, some extra content in the universe, I mean, we still need to explain the observational data. We cannot just put something to solve for example, the Hubble tension, and for example, disrupt the synthesis of light nuclei at the beginning of the universe. So we can use the cosmological observation to put constraints on those particle model physics, on those beyond standard model physics, actually. So we can, using the BBN, we can put upper limit on the lifetime of our decay, and also we can put an upper limit on the moderate to Doppler mass ratio using the CMB, because we know that the dark matter remains, they are produced in the beginning of the universe because of the long-lived particle decay, but we want that dark matter remains relativistic at the time of the CMB, so we need to have a lower limit on this moderate to Doppler mass ratio here. So using all these limits, we can use a Monte Carlo simulation, use CAMB, for example, to make, for example, to extend the parameter space of this model. So this model, this graphic here is very cool graphic, because in the horizontal axis we have cosmology, just the value of the expansion, the Hubble rate, the expansion of the universe today, right? And in the vertical axis, we have just particle physics parameters. So, I mean, this graph here connects cosmology with particle physics, and we show that varying this combination of parameters here, we can obtain a greater value of H naught from the lambda CDM model for different lifetimes here. So what we did as well, we studied essentially the what theory of the dark matter, what theory, effective field theory, can generate these types of decays. So we are assuming 3 different types. We are assuming a scalar dark matter, fermionic dark matter, and vector dark matter. And we construct the respective Lagrangians, dimension 5 effective field theory for each case. And we study, for example, how the mass of the dark matter can vary with the cutoff scale of our effective field theory in order to solve the Hubble tension here. This is using dimension 5 effective field theory. This here is using dimension 6. So I mean, we put some constraints here on the mass of the. Basically, these blue areas here are excluded by the lifetime, and so we have a region, a region space here, where each line here corresponds to a different value of delta N effective, right? So we make this study. This we are writing right now the paper regarding this dimension 6 effective field theory. Another very important topic, we study also considering now not just using more the CMB problem, the Hubble tension, but this is another paper we did. We studied the hadronic injection and the gravitini problem because of the decay of long-lived particles in the beginning of the universe. So since we are assuming extra content in the beginning of the universe, this can disrupt the formation of light nuclei. So we use the updated values of this, the values of the deuterium, the concentrations of deuterium, helium-3, helium-4, and lithium-7, and we put some new constraints on the parameter space regarding these injections because of the long-lived particle. If we have the gravitino, we can also constrain the mass of the gravitino with the reheating temperature in the beginning of the universe. So this is another paper we have did in the past, and another paper we made is considering non-minimal couplings and the relation of how these non-minimal couplings in the curved backgrounds can generate, for example, decays in the beginning of the universe. How can dark matter decay in the beginning of the universe because of the non-minimal couplings? So basically, we have here the Lagrangian of this is Einstein-Hilbert Lagrangian, standard model, dark matter, and we assume an extra interaction here, a non-minimal interaction between gravity and dark matter. Dark matter field here is phi, is a scalar dark matter. And if we go to Einstein frame, you can recast the Lagrangian, the standard model Lagrangian, in this form. This is just the usual standard model Lagrangian plus a correction term, where this correction term here have some interactions between the dark matter field and the usual terms of the standard model. In the sense that dark matter can decay in principle in the standard model particles. And we are studying using the projections of the CTAO, that is a collaboration. We use the projection of the new observations, and we put some constraints on the value of this non-minimal coupling parameter here that measures the strain of this non-minimal interaction between dark matter and gravity. And these are the actual this gray area here. All this here is the actual constraints, but since the CTAO are going to study a lot of a wider range of energy, we show, I mean, our study, our work can explore a unexplored region of this of the parameter space regarding the greater energy for the dark matter. That's CTAO are using like 100 TeV, a lot greater energy scale. So basically, that's all I have in my presentation. I have just to summarize. Particle physics is very important to understand cosmology, and we are working deeply in connection with the international community in the sense that we are looking to beyond standard model physics to explain these problems in cosmology. And I'm very grateful to be here at the Institute working with this phenomena, working with this matter. It was actually a challenge for me in the beginning because I never have studied. I have studied some of particle physics, but never worked with particle physics itself. So I learned a lot in this last year. So I'm very grateful to be here. And thank you, everyone. If you have questions.
Okay, questions?
So the ineffective thing, when I saw that you altered the radiation energy density parameter of the universe, but like I was thinking, how can you like alter the radiation energy density parameter of the universe that is so small in comparison to matter and dark energy parameters, and how can you alter that, and that comes to alter the Hubble parameter so much, like have a great consequence when you alter something so small in the universe?
I'm just getting there. There is some delay in the. Okay. It's freezed, right? So to answer your question, basically here, this is the graph I wanted to show. Okay, today we have the small amount of radiation regarding the dark energy and matter content, but in the beginning of the universe, the radiation dominates over the dark energy and over matter, right? So the idea is that this decay, this long-lived particle decay in this hot dark matter happens here in the radiation-dominated era, right? So it injects radiation, alters the radiation content at the beginning of the universe, and it evolves in time and changes the value of the Hubble parameter today. But it's because in the beginning of the universe, the radiation content is very, very strong. I mean, there's a lot more radiation than the other contents in the universe. And what I'm assuming is that there this decay here happened in the beginning of the universe and remains until these days, because that's basically the plot we need to make here. Right here, basically here we show that the energy over the mass basically need to survive until to this day. So we put a lower constraint on this moderate to Dogger mass ratio here, because if we do not have a lot of I mean, if this mass, the long-lived particle mass was not too much heavier, I mean, like you said, the radiation will not affect the CMB, all right? So we need to put some lower constraint on the mass of on this mass ratio here.
In such a way that we have way more long-living dark matter than the already decayed dark matter.
So long-lived dark.
in that ratio, you have way more chi prime dark matter than chi, so we have more long-lived dark matter.
I mean, not necessarily more dark matter, because we are assuming just 1%, but we have more energy. They are, I mean, the dark matter that originates because of the decay, they are more energetic.
It's heavier, like it's heavier.
Not, I mean, yes, the long-lived particle is heavier. In this, so the dark matter that are generated are more energetic, because heavier the matter, more energetic will be the daughter. The daughter is the dark matter, so the energy will survive until this day. So we need to put that's a very important question. We need to put this lower bound on this ratio here.
Okay, thanks. No, I got it.
More questions?
So I can ask a question. So it's related to maybe you can show the same plot. So as far as I understand, so adding more decays, you just basically shift the border where you change from radiation domination to matter domination, right? It's the other plot. That's the other plot where you had
plot?
Yeah, exactly. Right. So by adding more effects, you're just shifting this border between the blue and the red regions, right? And then you have these two curves, the blue one and the red one, which are basically the scale factor.
Yeah.
And this is where you will shift from one type of behavior to the other behavior, and this will affect, of course, what the value of the Hubble constant today, right? So probably the change that will be of the shift will be not that small, and that's why it will be actually compatible with the change of the proposed change of the Hubble constant today. I guess that would be the answer.
Hubble constant today used to be the same. What it changed was the Hubble constant in the early unit. That's the discrepancy. I don't want to change H0 today, but I want to change H0 to the early time to make the two measurements consistent. So the direct measurement prefers a higher value of H0.
Yeah, that's the same thing.
Is lower. So what I'm doing is raising this one.
Which means that you will raise one of the curves in this plot, right? So which will affect both of them, actually, today and tomorrow, and yesterday. Right.
Yeah, early times.
Early times, yes. There was probably kind of question or comment. I thought I had another one. Okay.
Okay, any more questions? If not, let's thank Matheus again.
Thank you so much.